Good day, everyone. Today we are going to study an important topic in computer graphics, geometric modeling, animation, CAD, and numerical mathematics. Both Bezier curves and B-spline curves are mathematical tools used to represent smooth curves. They allow us to create shapes that are difficult. You can find these curves in computer-aided design, automobile bodies, aircraft design, animation, fonts, logos, and many other applications. At first glance, Bezier and B-spline curves may look very similar because both are controlled by a set of control points. Let us begin with the basic idea of a Bezier curve. A Bezier curve is a parametric curve defined by a collection of control points. Suppose we have control points P0, P1, P2, and P3. These control points determine the shape and direction of the Bezier curve. For a cubic Bezier curve, 4 control points are used. And the curve can be represented using Bernstein basis polynomials. The parameter t usually varies from 0 to 1. As t changes, we move from the beginning of the curve toward its endpoint. One important property of a Bezier curve is that the curve normally begins at the first control point and ends at the last control point. The intermediate control points influence the direction and shape of the curve, even though the curve does not normally pass directly through those points. One of the most important characteristics of a Bezier curve is global control. If we move one of the control points, a large portion of the curve, and sometimes the entire curve, may change. For a small curve, this is not a serious problem, but for complicated designs, changing one control point can affect the shape far away from that region. Now, let's explore the solution that B-spline curves offer. B-spline stands for basis spline. A B-spline curve is constructed from control points and B-spline basis functions. The general form uses basis functions represented by n sub I, p of u. The most important difference is that a B-spline does not require every control point to influence the entire curve. Instead, each basis function. This gives B-splines a property known as local control. Now we reach the central idea of today's lecture. The core difference between Bezier and B-spline curves is their control behavior. Imagine an engineer designing the body of an automobile. If one small section is too wide, the engineer wants to adjust that section without destroying the rest of the design.
As the number of control points increases, the degree of the Bezier curve also increases. High-degree curves can become mathematically and computationally less convenient. B-splines solve this problem by allowing many control points while keeping the degree relatively low. For example, a cubic B-spline can have 20 control points while still remaining cubic. The knot vector is one of the most important concepts in B-spline mathematics. It determines where polynomial pieces begin and end, and how the basis functions influence the curve. A B-spline is generally a piecewise polynomial. It can be understood as several polynomial pieces that are smoothly connected. Each section can have its own polynomial description, but the sections are joined together smoothly to create one continuous curve. B-spline basis functions are active only over certain parameter intervals. Therefore, only a limited number of control points contribute to a particular point on the curve. For a B-spline of degree p, at most p+1 are location. Therefore, for a cubic B-spline, 4 neighboring control points generally influence a particular point. Another important difference involves continuity. B-splines are naturally designed to join polynomial pieces smoothly, depending on their degree and knot multiplicity. Smoothness is extremely important in geometric modeling because abrupt changes in curvature can affect its appearance, manufacturing, aerodynamics, and mechanical performance. Another major advantage of B-splines is that we can increase the number of control points without necessarily increasing the degree. We should not conclude that B-spline curves have made Bezier curves useless. Bezier curves remain extremely important because they are simple, intuitive, and easy to implement. When the shape becomes complicated, B-splines become increasingly attractive because they provide local control and allow designers to manage complex shapes efficiently. Bezier curves generally provide global control and use Bernstein basis functions. B-sp and use piecewise polynomial basis functions determined by a knot vector. To conclude, Bezier curves, B-spline curves emphasize local control and efficient representation. These concepts become much easier to understand. Thank you.